in our discussion on magnetism, we're going to look at self and mutual inductance and how inductors work inside a circuit. So I'm looking at our picture here, self-inductance. So we know that when we have this blue current going in the direction that it's going, you can take your right hand, your thumb is going to point down in front of the core, your finger curl is going to point inside to the right, which is why we get the red magnetic field that is induced by our blue current. So that's what we get, and we've done that with an electromagnet. Now, what we're going to look at is what happens if we start to change this blue current, because as soon as I change my current, I am going to change my red arrow for my magnetic field. And since I have a coil of wire and I have an amount of magnetic field coming through, or flux coming through, as soon as I change that flux, right here we have an equation. Change the flux, you end up with an EMF. So, well, I already have some current there. Yes, we get a second EMF that is produced, and that EMF is either going to add to the current that we already have, making it bigger, or it is going to oppose this current and make it smaller. Now keep in mind, this is only going to happen when the flux is changed, whether it's current or whatever else. Once that flux begins to change, that's when this happens. So I have it written out here. When the current changes in the coil, the flux inside changes and creates a self-induced EMF which tries to stop the change that is creating it. We can use the right-hand rule to figure out which direction our EMF is going to point compared to what direction our current is. And one way to think of this is current inertia. So basically, our induced EMF right here is simply going to oppose the change. So if I try to turn the current up, if I try to make the current bigger, I'm going to have an EMF that opposes that arrow, trying to reduce it. It doesn't prevent it, it just slows the process. If I try to turn the current down, the EMF that's going to be induced is actually going to point with the current. So even though the current is dropping, the EMF it pushes along with the current, trying to keep it going. Again, it is going to change. The self-inductance is just going to reduce that rate of change. So I've got the Bunny equation for the magnetic field through our coil here. This is our coil density, which is the total number of coils divided by L. So now we've got our flux here is going to be B multiplied by our area. So we have our area there. And now we know that we have our EMF is going to be a change in that flux. So we can bring this down and do our change. Our change is going to be as the current changes. So I pull I out, and that's what I get right there. If we scroll down, you can use your right-hand rule to figure out, to prove these two statements, that if I is decreasing, we end up with a positive induced current that goes with the original direction of current. So again, this pushes with the current, trying to stop it from decreasing. And here we end up with a negative current, which is trying to stop the increase. It does not succeed, but it does manage to slow the process. If we put them into a graph, if we look at the current versus the, if we look at the flux versus the current, our slope is going to be the self-inductance. So we can put that together here, and we end up with an equation, y equals mx plus b, and this is how we calculate the self-inductance. We look at how many coils it has, what flux we end up having. We can figure out what the flux is by doing B times A, B dot A, I should say, and dividing it by the current. Right. And so I scroll down a little bit further. Our unit is going to be our flux divided by our area. So, not our area, I'm sorry, our current. So we end up with our flux divided by the current, which is a Weber per amp, which we call the Henry, capital H. We don't use this very often, but it is a unit, the Henry. We can go millihenries, microhenries. And again, the purpose of this self-inductance in terms of how we use it is it slows down any changes. So, and continuing our work over here, so that's from our graph. If we look at the rate of change between them, so if I look at the rate of change of flux and the rate of change of current, we recognize this right here as our EMF, and so that is our equation. One of the things we'd use is a surge protector. A surge protector is designed so that if you have kind of more of a old school, when you have your old school computer that's always plugged into a wall instead of a laptop kind of a thing, but basically if you have anything that is electric plugged in and you had a sudden surge of electricity, be it from a lightning bolt or something else, that could damage your equipment. So what does a surge protector do? It's quite literally a coil of wire in a box. And once your current, if your current is constant, it's just a wire. As soon as the current tries to change, whether it's turning something off or a sudden increase in current, this coil actually slows down that process and it restricts how much current you're going to gain. And so, so that's what our inductor is. So there's our inductor. We call it a choke. It actually is the same thing that you're thinking if you've heard of the word choke when it comes to engines. It's the same thing, and we can talk about that in just a little bit. After self-inductance, we have mutual inductance. So basically what I have here is I've got two coils that are near each other. We always show a picture like this with some kind of a core and some coils here and some coils there. We get our magnetic field B. But it doesn't have to be that way. You can just have two coils that are just near each other. You can have one coil stacked on top of another. You can have two coils that are kind of interwoven into each other. You can envision taking these coils and simply sliding them in so that they're kind of overlapping. But what I have is I've got my primary coil coming from some primary source, and I'm going to get a current over here that's going to be induced. And so if you watched any of those videos from the previous week, they're really good videos about the different types of uses for inductance. But this is wireless charging. I have one of those in my classroom. I was at a white elephant party, and white elephant parties are everybody brings a gift, and it's like a big random gift exchange, and you can steal. Someone had two wireless chargers, and I thought, physics, let's get those into the classroom. So if you remember the wireless chargers I had sitting in back, it's because I decided to select that gift and stole it from a friend of mine. But anyway, that wireless charging, whether it is your phone on a little wireless charging mat, whether it's an electronic toothbrush that sits on a little stand that gets charged up, lots of options, lots of ideas there, and that's how you end up with that charging method. So if we come down here, we can look at the flux going through the second coil from the current of the first. So if I increase my current, I increase my flux, I get a nice straight line. And just like we did before, we are interested in a change in that current and therefore a change in that flux. And so if we come down here, so we've got this equation right here. So instead of L, it's M for mutual inductance. And we can kind of squeeze everything together, do some algebra, and kind of look at how many coils do I have in the secondary, how big is it, and what is that flux going to be caused by the first. So we can kind of put those together. When it comes to magnetic field energy, so we have energy from a gravitational field. We have energy from a changing gravitational field. We have energy from an electric field, and so on. So it shouldn't be a terrible surprise that we have the ability to store up energy in a magnetic field. So what we have here is we've got our power equation, which is the rate of change in energy per time. So we call that, we use the unit of the watt, how much electricity is how much energy is given off every second. So if we rearrange this and we look at our power is I times V. That's from a couple chapters ago dealing with electric current. So if we take this and apply our EMF equation right here. Remember, EMF is a potential, it is a voltage. So the EMF right there, we can plug that in, and we end up with this that we can put over here. We can now do an integration. So when we put this up here with our dt, we have the dt canceling out. And so when we do our integration, all we're integrating is a constant L and then I di. So we know that we increase to a power of 2 and divide. 1/2 Li squared. We see this a lot. A 1/2 something squared. We see this a lot, whether it was springs, whether it's kinetic energy, etc. So we see this quite often. We had the same thing for capacitors. So this is going to be the energy stored in an inductor. So think about it. You turn on the power to your surge protector. It's going to increase in current because you just turned it on. Your surge protector is actually going to momentarily try to slow down the process of it turning on, and that is in turn storing energy. And then what happens later on when we lose electricity? That energy is now going to be used to continue. So if I just flip the switch off, that coil is going to continue pushing charges because it's trying to slow down the change. And so we end up with that energy being used. Energy density, you can read through this one. It's basically just one of those, half-day concepts that's in the book. We discuss it and we don't use it very often. This would be kind of like a multiple choice kind of question, but our density is going to be the amount of energy that we have stored up divided by the volume. Our volume is going to be the area multiplied across the length. Our energy, we have an equation now to figure out what that energy is, 1/2 Li squared. And so you can kind of put all those things together. Things cancel out very nicely, and you end up with something like this. We don't use that very often, so we're going to skip it. So now we start getting into our different types of circuits. So we've had circuits that had resistors in it and batteries in it. We did Kirchhoff's laws. Then we had RC circuits. What happens when we have a capacitor and how long it takes for it to charge up, and time constants, and all those different sorts of things. Well, now we have inductors. We have L. So this right here would be an RL circuit or an LR circuit. That's kind of used interchangeably, so you can look it up in your book and see what they like to call it. But anyways, we still have the loop rule. Loop rule is always going to work, always. So we end up with an EMF from the battery, resistance being taking some of that potential and using some of that potential up, and then we have our newest, the EMF in our inductor. And again, we need a rate change in our current. Let's just say a change. We need a change in our current. If we know what that rate change is, we can use that as well. And that's going to use up some of it because it's going to be gaining energy at the beginning. So at the beginning, our switch is open, we have no current, and then we close it. Our current is 0 because this is restricting the current and slowing down the increase in our current. It's almost the opposite of a capacitor. Remember, a capacitor, we turned it on and immediately we had full current. And then as time went on, the capacitor slowed the current down. This is the exact opposite. This is trying to keep it at 0 until the current builds and builds and builds. Like I said, it doesn't keep it at 0, it just slows it down. So scroll on down here, and so what happens is that right when you close it, there is no current. Our resistor is using up 0 of the potential, which means all of our potential is right here. After a long amount of time, the current isn't stopped, it is slowed. So it still increases, and eventually it's going to reach its maximum. And we said that once you are at a maximum current, your coil just behaves like a wire. It doesn't do anything. It's only when you change the current that it does something. So we have our maximum. It's a constant, which means our rate change has dropped to 0. So now that voltage is 0, and now we just have Ohm's law, V equals I times R. We have energy now stored up. So when we turn off the power, we still have an EMF. We still have some energy that's going to be able to drive charges through the system. So I can see that I'm going to have some maximum. It's going to take us some time to get there. So if we did some work, I'm not going to talk through all of this, you can look through, but this is for our RL circuit. So if we want to figure out the amount of current we have at some time, some actual time, we can go through and do this. And I'm going to give you a little spoiler here. It's going to look very, very similar to us figuring out charge Q inside our capacitor. So here we go. So we've got our Ohm's law, we've got our inductor, and so what we're going to do is we are going to try to get all of our I variables together. So we've done that up until this point right here. We've got our I variable together. We want to try to simplify that, so we continue down, and we've made our I variables as simple as we can right here. Got everything else on this side, they're all constants except for time. So when we integrate, we just get time on the left, and then we have to integrate on the right. We can do our U substitution for that, and we end up with the natural log of our lower function. So now we go back to the top. I've got two columns for this particular thing here. And so now what we can do is we can plug in our current was 0 at the beginning, and then current is going to be eventually I. We go through, do all the same things we did for our capacitors, and we end up with right here. So we've got our work through here, and as we come down, we get something very, very familiar. 1 minus e to the power. Time is up here. A negative sign is up here. This all makes a lot of sense. Let me rephrase that. It might not make sense. This looks familiar when we compare it to what we were doing with a capacitor. Scroll on down. We had a time constant before involving our resistor and our capacitor, our RC circuit. Well, now we have a new time constant. This is the same symbol, time constant, and this time constant is going to give us a percentage of the total current that we're going to end up with. What percentage of that do we have here? This being the total, because this is Ohm's law. And L over R represents our time constant. So this actually ends up being negative time over our time constant. Negative is going to give us the proper function there. Come down here, and how is it that a Henry and an ohm, how is that going to give us time? Well, if you go through and you look at everything here, you have a Henry, which is our flux per amp. Amp is coulombs per second, so this has a second in there. And as you go through, you get seconds. So you can, like I said, you can go over that, and you can see where that all comes from. So kind of seemingly unrelated. So if we have an LC circuit, and this is purely theoretical because you always have some resistance in your wires, right? So if we have no resistance, so maybe you got a superconductor or something like that, but if you have no resistance, what you're going to do is you're going to close S1. So closing S1 just gives us a capacitor system. So this E is going to immediately charge this up because there is no resistance. Charge can flow as quickly as it needs to. So we get this thing to charge up. We can figure out the charge stored up. We can figure out the energy stored up. We can do all of that. Open up S1, and this is now stuck where it's at. I've got a little picture here. I've got a positive plate on top and a negative plate on bottom. Now what we're going to do is we're going to close this switch. We've got a capacitor driving charge off the top plate over and around. We have this, which is going to try to slow down the process of that increase in current. So coming down here, we get a clockwise current driving it through our inductor over here onto the negative plate, and we know this is going to continue to push until the plates are neutral. So at time 0 we have no current and we have full charge. Charge is going, the current is going to increase even though the inductor is going to resist it. Our current is going to increase, and that increase in current is coming from the energy that we had stored up from our battery going into the capacitor. Now that energy, as those charges, as they move through the inductor, that inductor is doing work on those charges. It's gaining its own energy. So this energy is turning into this energy down here. And if we continue to watch what's going to happen, we are going to go from this initial condition to where this thing has no more push. Once we have no more push, we have achieved our maximum amount of current. And since it's not going to push anymore, the current's going to begin to drop. But what is that inductor going to do? It is going to now all of a sudden go from trying to stop an increase in the current. Well, now the current's decreasing. And now the inductor tries to stop the decrease. And so the current should stop here. The inductor keeps it going. And so what happens? Charge continues to flow until I get a positive buildup on this plate. And then what happens? The inductor, after using up all its energy to continue driving charges forward, that inductor has put all of its energy back into the capacitor, which is where the energy had originated, if you don't count the original battery. And then what happens? Now the positives are going to flow counterclockwise. It's going to get to a point where all the charge has flowed off of it. Maximum current. The inductor keeps the current going after that, and it builds up on this side. So it's this back and forth and back and forth. Energy goes from the capacitor to the inductor. The inductor keeps the charge going, puts it back onto the capacitor. The capacitor has that energy pushing charges. It loses it all. It gains it in the inductor. The inductor keeps the charge moving and back and forth and back and forth and back and forth. So what you have is you've got simple harmonic, well, do we have simple harmonic motion? We end up with an oscillation. And remember, I know it was a long time ago, whenever we have oscillations, we come back to this scenario, we come back to this model. Can we make a model that looks like this? And by looking like this, what I mean is we have MA equals KX. A is the second derivative of this function right here. And so remember, simple harmonic motion means that our acceleration was proportional, our force, and therefore acceleration was proportional to our displacement. So can we get something like this? So this right here is the loop rule. I only have the two devices because we have charged it up previously. So we work our way through and we end up with our current is the rate change in Q. So this right here is the change of I. I has a change of Q, so this is the second derivative of Q. Here's Q, and so yes, indeed, what we find is we end up with our variable, the second derivative of our variable, and our variable over here. We've got L and C instead of K and M, but I can see the similarities. So we do, in fact, have simple harmonic motion. Our simple harmonic motion equations look like this. Instead of X, which is our displacement, we have Q. Maximum displacement, maximum Q. And everything else is still related back to time. Omega, we get here. And all we have to do is take L and C and compare it to K and M, and we end up with something that looks like this. We can do integrations. We can do derivatives to get the next equation for current. We don't really need to worry about anything beyond that. And then we've got our energy down here, just like we could do energy with springs, we could do everything. So basically we're just stealing all of our spring energy stuff that we did before and replacing it with the electrical equivalents. So looking here, so you've got your charge is your X, your rate of change in charge is your current, which is the same as the velocity. So M was the mass, right? And mass is Or inertia. Inertia is the resistance to change. That's exactly what this is. It's resistance to change. And then K was going to be the strength of our spring. The stronger the spring, the quicker things snap back. Well, this right here is our storage space. The more storage space I have, the longer things are going to take. So I see an inverse relationship there. So you can use all of our simple harmonic motion framework, and you can simply bring over your LC circuit info as well. And let's see, the last slide we're going to look at here is what happens if there is resistance, because there's always resistance. Simple. We just slowly lose. So we get this oscillation back and forth, but it is a damped oscillation. It is slowly losing energy, and we know that resistors turn the energy typically into heat. So we lose energy to an unusable form, at least as of now. We don't have a real good use for that little bit of heat that's built up, and so we lose the energy, and the system oscillates down and eventually levels out at zero. There's a few other slides on here that are some examples and some pictures and things that we don't really need to worry about. This is last year's slideshow because I don't have my big whiteboard at home, so I can't update it, so I'm just using the old ones. So that's the end. So that's taking our inductance that we learned last time, which is how we develop most of our electricity in this country, the holes in the wall, etc. And then we took that induction and looked at self-inductance, which is a resistance to change, L, mutual inductance, which works really well for our wireless charging, etc. And that's everything. So this week is simply finishing up your onlines. I have a tentative due date of June 4th, just because June 5th is your last day. But I can open it up through the weekend, so that's not a problem. But I'll let you request any extensions that you might need. So with that, I'll see you at the Zoom meetings, and if you have any other questions, make sure you send me a message. It's been fun. It's a little bit of a unexpected ending of the year, but it's been enjoyable being your teacher. So hopefully you can take this information that we've been using all year long, including this last little bit, and you can put it to good use in your future classes.